going to start here by finding the vertical asymptote. To find the vertical asymptote, we take our denominator, we set that equal to 0, and we solve. So setting my denominator equal to 0, solving, I find that x equals -7. At this point, I'm looking to draw a conclusion about the vertical asymptote being x equals -7. So I could go ahead and set up my therefore statement down here and say x equals -7 is the vertical asymptote. But the thing about this problem is I have to justify it with limits. So how I justify it with limits, I take the limit as x approaches this value that I found of -7. I approach that from the left as it's applied to this function. And then I take the limit as x approaches -7 from the right as it's applied to this function. So we set up a left-hand limit, we set up a right-hand limit. We evaluate both of those limits by going to the graph of the function. If I go to the graph of the function, see the asymptote there at -7. We can see from the left, graph is trending upwards. We can see from the right of that asymptote, graph is trending downwards. So from the left, it is going to positive infinity. From the right, it is going to negative infinity. All we're trying to do to justify that this is a vertical asymptote is show that with the left-hand limit and right-hand limit, we're getting something infinite back. We have shown that. So this conclusion we've drawn, this therefore statement we spelled out, would be true. For the horizontal asymptote, figure out what the horizontal asymptote is. What we do is we apply a limit as x approaches infinity, and we apply it to the function. Now I could say f of x, but because I'll be interested in exploring degrees here, let me go ahead and spell out the entire function of 2x over x plus 7. Whenever we're evaluating a limit as x approaches infinity, we apply our little degree rules. We look at the degree in the numerator. Degree in the numerator would be 1, because that's the highest power of x. Degree in the denominator, also 1, the highest power of x. Since the degrees are the same, we divide the coefficients on those terms that gave us the degrees. So we take 2, we divide 1. This limit would equal 2. With horizontal asymptotes, we appreciate if we take the limit as x approaches negative infinity, applied to the same function. Same rules would apply, same value would result, meaning, we draw a conclusion here, y equals 2 is our horizontal asymptote. And this is one where if you wanted to check it against the graph, we've already graphed this out to look at the vertical asymptote. You come back here, you could go to your y equals screen, you could type in 2, the horizontal asymptote that we found now. Type that in the second line. Graph it out, you should see it slicing right through. All right, we're going to apply the intermediate value theorem to find a root on the given interval. So part of the presentation here in part A is we have to actually be able to state this theorem applies. So how we know this theorem is going to apply is we begin by saying our function is continuous, and it's continuous on this interval that's given of 0 to 3. A lot of these problems we did, it was all real numbers, but here we have a specified interval, so we'll run with the interval itself. After this, what we do is we take these values that make up the ends of the interval, we plug them into the function. Plug them into the function, see what we get back. What's nice about a given interval is you already know what numbers you want to work with to plug in. Before, when we had all real numbers that we were playing with, it's a little more spread out. We had to do a little more trial and error. But here, if I just take 0, I take 3. Got to plug in my function first. Should have my table set up and ready to go. Well, it looks like I have 0 left over from the last time we did these, and I'm plugging in 3 as well. Got that up there already, I know. But if I plug in 0, I get 8 back. I plug in 3, I get -1 back. What that shows me now, if I'm talking about a root, I'm talking about a root in the sense that if I take some number C and I plug in, I get a value of 0 back. So these numbers right here should be values that surround this number up here I'm supposed to be getting back when I plug into the function. So it should work out that way with the given interval. Since it works out that way, what we do is we state that we understand these numbers surround that value of 0. So we say f of 3, which gave us -1, is less than 0, which is less than f of 0, which was 8, right? 0 falls between those two. Therefore, this is where we can draw the conclusion that we can use this theorem. We say by the intermediate value theorem, there exists a number C on this interval. Now, if you want to write that all out in words, you can, or we could just do this. There exists a C on this interval 0 to 3. That's all our formal presentation for this problem. Now that we've established this theorem is going to hold, for part B, we're going to actually find that value of C where if I plug into the function, I get 0 back. I find that C is a root. So to do that, I'm going to take C, plug into the function. Plugging in the function, replacing all my x's, I get c squared minus 6c plus 8. F of c is supposed to equal 0, so now replace f of c with 0. 0 equals c squared minus 6c plus 8. And from here, if I solve for c, that's a problem we could factor, right? But we've seen situations on these types of problems in the past where it hasn't been so easy to solve, right? So let's review once again using the calculator how we would find this value of c. I know I can factor that out pretty easily, but if I go to the calculator, I've plugged in my function, right? 0 equals this same thing I have up here for y equals. If I graph this out, we're working on the interval from 0 to 3. So from 0 to 3, here's x is 0, here's x is 3. I want to focus my attention in on the x-intercept right here. Now, it should be obvious what c is, right? But in case it is not, what we do second trace, we hit item number 2 for 0, and we line up to the left of this point we're trying to find. We line up to the right of that point we're trying to find. Enter one more time, and we find the 0 is 2, so c would equal 2. If we're going to find the equation of the tangent line through this point, let's find that equation in point-slope form. So I could start by writing out as much of this equation as I know. I could start by writing y minus the y value at the point equals the slope, which is the big problem here, trying to find that, times x minus the x value at the point of 5. I know that all of this right here is going to make up my answer. I just got to find the slope. So how I find the slope? I go to the calculator. In the calculator, I enter in the function. I've got x plus 1 divided by x. And then what I do, in my second line here, I let this y sub 2 idea be my slope formula. So I set up some parentheses. Reviewing how to do this again, we go to the variables key. We go to y variables there at the top. Hit enter for function. And what you want to do is you want to call down y sub 1, so you hit enter one more time. You've now brought down that first line. You take that y sub 1, you subtract the y coordinate at the given point. Close the parentheses. Divide that by, new set of parentheses, x minus the x value at the given point of 5. So now I'm going to go to my table screen. And on the table screen, well, let's see, I don't have any given x values here, right? But if I look at the x value at the given point, the x value at the given point is 5. So I should choose numbers for x that are getting closer to that value of 5. I could start at 4, go to 4.5, go to 4.9, 4.99, and so on. Punch those in. I've got my y sub 1 column here. I got my y sub 2 column here, which represents my slope. I want to see what these numbers are trending towards. So 4 goes in, 4.5, and so on. Let's see how we're doing here. Pretty good trend, right? If you need to carry it out further, we could add an extra 9 in there. But let's say I round this off to a couple of decimal places. These numbers are trending towards, looks like, 0.96, right? So I could summarize that over here in this column, or just say, hey, I know this is rounding off to 0.96. If that's rounding off to 0.96, then I know my slope is 0.96. I fill that in over here. I've got my equation for the tangent line.